Hello, and welcome to part one of a two-part webinar series where we'll explore the use of sophisticated digital analytics techniques to help highlight remaining exploration potential in the North Sea. The first webinar is going to focus on the key steps of providing a trusted and standardized dataset to allow the application of machine learning. The second webinar on the 9th of June will focus more on the data analytics and the use of machine learning to identify pay zones. First, I'd like to say a big thank you to the 4 technology companies who have done some amazing work and overcome a number of challenges, which you will hear about, to bring us to this point and made these events possible. Our project sponsor companies, who have provided guidance through the portfolio steering group and individually to the technology companies along their projects. And finally, to the other supporting companies who have provided data to make all this possible. As you can see, this is truly an industry-wide cross-border collaborative effort. So before we get started on the projects, I'd first like to tell you a little bit about the OGTC. The OGTC is a not-for-profit organisation that was established in 2016 with 180 million of funding from the UK and Scottish governments. Our purpose is to unlock, anchor, and inspire innovation and transformation. We work by partnering with industry, academia, and the regulator to deliver innovative technology through technology roadmaps that address key challenges identified by industry. So the initiative you're going to hear about today was sparked by the Exploration Task Force, who wanted to explore how the use of digital analytic techniques, such as machine learning, can help to highlight and high-grade remaining exploration potential in the North Sea. The time remaining to discover commercially viable hydrocarbons in the North Sea is rapidly diminishing as key infrastructure hubs are considered for decommissioning. The use of artificial intelligence and machine learning to augment the capability of subsurface teams to analyze and assess large volumes of structured and unstructured geological data faster and with less human bias is one key to unlocking this yet to find potential. Mature fields have a legacy of data in many formats, often sourced from diverse siloed application-specific archives of various vintages and whose quality and metadata are typically not consistent. Efficient and cost-effective data gathering and conditioning into a single platform is needed, where the resulting trusted data can be quickly assessed for strategic decision-making and automated AI-enabled interpretation to help rapidly identify any incremental reserves. So an area in the northern North Sea was selected for the pilot study. This area was selected since understanding at a high level of screening the level of remaining exploration interest, including overlooked opportunities, was required because this could feed into area plans where several decommissioning decisions were fast approaching. The geographical area is also ideally suited to the application of machine learning techniques, as it contains over 7,000 exploration and development wells available in the public domain, both in the UK and the Norwegian sectors. So the OGTC sponsored 4 technology developers to tackle this challenge. As you can see from the slide, each company approached different aspects of the challenge. The first company you'll hear from today, Sword, concentrated on the data conditioning step. The second company you will hear from today, Energective, tackle the challenge from end to end, applying their own data conditioning approach, followed by automated interpretation to that data for pay. They will describe both of these aspects in their talk. The other 2 companies, Merkel and Keeler and Earth Science Analytics, concentrated purely on data at the automated interpretation aspects using the dataset generated by Sword. This will be covered in part 2 on Tuesday, so please register if you haven't already to hear more about these 2 projects. So I think so. This approach was taken. So by supporting different projects, we are able to get we're able to compare the different approaches, and see how the different results. And also, we generated these deliverables here. We have 2 condition data sets, and we'll generate 3 sets of data from the data analytics to see how they have managed to identify new existing and new pay zones. So as part of the deliverables, the condition data will be made available via the OGA data center. More information will be given on this when it is ready. So please watch out on social media and our website for more information on that. The results from the analytics will be made available after a period of review from the sponsor companies. So please keep an eye and ear open for that also in the coming months. So before we start, a couple of housekeeping rules. The webinar is being recorded and will be available through our website, most likely in a couple of weeks' time. After each presentation, there will be a short Q&A session, and I will also provide contact details of the presenters at the very end of the webinar if you would like to carry on any conversations in private with them. During the presentation, all attendees will be muted and the cameras will be turned off. Attendees can raise a hand to ask a question or use the chat box function throughout the event for the Q&A session. The attendees' questions will be managed by myself, so when the Q&A comes around, if you want to ask a question, just use the function to raise your hand and I will see that and I will be able to unmute you so you can ask the question. Alternatively, like I said, please just type the question into the chat box and that can be asked through that medium as well. So I think that is enough for me, and I think actually I forgot to introduce myself at the beginning of this. My name is Ian Martin and I'm the project manager at the OGTC for the Subsurface Solution Centre, and I'm sort of really pleased that we have so many attendees here to listen to what at the OGTC, what we feel are really have been really exciting projects to and getting the results from these is a real big milestone for us. I will now hand you over to Chris from Sword, who will present on creating a standardized and trusted data set ready for machine learning.
Thank you, Ian. I'm just going to quickly share my screen and then I can get going. Okay, can everybody see that? We're good? Your thumbs up?
Not yet.
No? How's that?
That's good.
Good, okay. Hi everyone. So thanks, Ian. And firstly, I'll probably say thanks to the OGTC for sponsoring this project and allowing us to do some really interesting work. So what I would like to do is I'll first go through kind of who Sword are, what our kind of strategic view is on this kind of work, and go through the case study of what we've done, look at some results, and then look at how we've taken the work on that we've done and actually applied it elsewhere now within the industry, because that was one of the key aims that we came through this project to do, to build technologies and to be able to take them on and make something that was reusable and beneficial to the industry as a whole, not just as part of this project. There we go. Okay. So yes, I'm the data analytics lead for Sword Venture. I was with Dataco up until around 6 months ago. We started out this project as Dataco, and then we were bought by Sword. And since then, we have merged with Venture, who up until that point were probably one of our biggest competitors, which meant that coming together, it's given us a really strong kind of a strong platform to build on both companies. And the strategies going forward align very well in the space of what we've done in this project, and we've been working really hard to try and enhance what we were able to do in this project and technologies that we had before this. As you can see from the slide, we're mainly UK based with a office in Rijswijk and one in Perth. And so if you don't know anything about Sword Venture, what do we do? Mainly we're data and information management, but we are augmenting that mainly with analytics and technologies. We do some things around geospatial and regulatory compliance, and we also have petrophysical services, and we have a number of clients. And our focus, our kind of strategic focus, is definitely on the digitalization and the utilization of data analytics in the data management space. We've seen a number of challenges in digital transformation just through the work that we were doing since, during, and before the OGTC project. The need for access to quality data, especially within when we're trying to do machine learning, or even when we're just trying to work with large data sets. Over the last few years, there's been squeeze on IT spends in the industry due to the downturn and other factors. We need to demonstrate payback from digital transformation. So we're hoping that these technologies will allow companies to do this, not just go for the low-hanging fruit. And the lack of data that's available for digital transformation and is data science ready is, is quite a big gap in our industry. So we really just want to make the data available to the right people at the right time. So that was the primary focus of what we were trying to achieve here. Our view is a kind of a three-part view. We want to liberate legacy data, understand the legacy data, and use this to augment workflows and take things that were maybe 5-10 years ago fully manual processes and turn them into as near to fully automated processes as we can. And we understand that this is an iterative process and something that we're going to have to work on for the foreseeable future, but this project has given us a great start. So as Ian said before, we kind of fit mainly within the data conditioning phase. That's where our work ended. So the wider deliverables, I'm sure that everybody here is aware of what they were, but we stopped this project when we created a clean conditioned data set that was ready for machine learning, mainly for Merkel-Aquila and science analytics. Colin will give his overview of the Objective project, which took it from beginning to end, which meant the data conditioning phase for us was probably slightly different to them, due to the companies that we were working with. We had Earth Science Analytics, who are an inside industry, domain specific, I would say, machine learning company. They have a good platform. They understand the data types. They've grown from knowing the industry. And we've got Merkel-Aquila, who are a new entry to the oil and gas industry. And I think it's fair to say that some of the data that they were dealing with was a little bit of a shock to them in terms of the bar to entry. It's different to a lot of other industries where you might be dealing with an API or a constant data stream or time series data. The legacy data is difficult to deal with. So this gave us a kind of a unique challenge compared to what we're used to, making a data set that was usable for a company that never worked with this kind of data before. So our scope is in 6 parts, I guess. So we undertook an ETL process to incorporate OGA's data, the MPD data, and data that we received from 8 different operators, which was around 7 terabytes in total. We discovered and digitized all available CPI logs that were not already available. That was mainly in the OGA data set. The MPD data set actually, I think, requires that. We created JWLs to digitize high-value raw petrophysical curves. And this gave kind of a starting point for both companies, that we delivered a joined well log for every single well that was in scope that had data available. Everything was standardized and in a format that was easily digestible into their platforms. We worked to discover and extract tabular data and make this available via CSV and JSON format. We worked with some natural language processing to standardize information from formation tops, and we create a standardized QC'd well deviation data format. So what does the data look like? Well, as you can see, it might be a little bit small, but we've got data ranging all the way back to 1969. And the amount of data that is being created today, you know, is quite a lot. But you can see that, you know, the data vintage all the way back to the mid-80s was pretty steady. So the range of data that we were dealing with was quite large, and this obviously gave us a number of, when it came to standardization of this data set, it gave us a few challenges and quite novel approaches that we had to make to be able to do this. This kind of shows, again, when we look at the age of the drilled wells, even though a lot of the data has been created in the last 20 years, a lot of the wells were actually drilled historically. So there's kind of an inverse relationship between, you know, the amount of wells that are being drilled and the amount of data that's available for them. We saw some interesting things, such as you know, DLIS files coming in the last 5 years that have got hundreds of curves in them, and then going back to the 70s where you've got one last file with maybe 3 or 4 curves. And the disparity of the data set meant that creating one workflow to cover all of these data types was challenging. So we split this into 2 main parts: the well log data condition and standardization. We built a workflow where we would do proximity analysis to try and find wells that needed data made digitally available for them, identify the wells, create a gap analysis of what data might be needed, digitize that data, create an automated log splicing algorithm, assimilate that and standardize that, and then populate that to our database. The unstructured data part of this, when we were looking at mainly PDF, TIFF, and ASCII data, was split into two parts: tabular data and unstructured data. So we did data extraction and data mining of the tabular data, and we did information extraction and text mining of the unstructured information. So the technologies that we used a combination. We used a combination of cloud services and APIs, but we also used our own development stack, which was mainly Dataco's development stack, as we did most of that. But we've actually brought quite a lot of the technologies that Venture are using, and we're still working on to kind of build that stack up. And we've taken the approach that there are APIs out there that are available from these cloud platforms that are really great for undertaking this kind of work. So there's no point reinventing the wheel. Let's make use of those, but let's also stick to, as much as we can, making these technologies out of open source data sets. Open source interfaces, and use those to build something that is kind of reusable in the future. So looking at the tabular data extraction, we had three main considerations in this. We've got data that's locked into image or PDF format and is not machine readable, which is no good for a machine learning project. We've got semi-structured data, which in many cases followed the very loose format types. And we had colloquial lexicons used for formation descriptions, meaning that it was a little bit difficult to make one kind of coherent data set in that. So we split this down into 4 parts. We undertook a document OCR. We used machine learning for data extraction. We undertook text analytics, and then we did some data type mapping. So for the data extraction from reports, this is something that we are currently still working on as part of phase 2 of this project. So none of the results of this part will be made available with the first data package, but should be made available probably within the next couple of months in the second data package that we'll deliver to the OGA. So we are looking for permeability and porosity data, pressure data, and shows data with a possible expansion to deviation and lithology data within PDFs and TIFF reports, end-of-all reports, or whatever reports may be available in the corporate stores. And you can see the data challenges here. We're working with data that can range from what's on the left to what's on the right. You know, data it's still there and it's still available, but what you can get out of it is, you know, even the best OCR engine might struggle with that, all the way through to data that's very modern and might even be in a PDF format that can be extracted using more generic technologies. So to do this, we've taken a 3-step process: document preparation, using OCR evaluation and doing image conversions. We then have built a convolutional neural network that is basically trained to find tabular data within each page. That data is then OCR'd, sent on to a classification model, which then classifies which data type that table is for. That is then sent onto an API and then rebuilt and populated to a database so that we have that data digitally available in a CSV JSON format, which is structured with a database that sits on top of it. So we just spoke about working with reports and working with really unstructured data. We then needed to work with the digital data that was available, mainly from this problem kind of sat across both data sets, so both NPD and the OGA's data sets. So we had some loose formats for well paths, P72 formats, but there's a lot of data. There was a lot of those that have, I guess, been I wouldn't say tampered with, but only loosely follow those formats. They may have been changed. They may have been through different softwares. They may have been uploaded without proper validation. A number of data formats on the Norwegian side that were difficult to parse. So we used a machine learning approach to basically split data and headers, map columns, and then do a statistical data QC to fit that data into the database and have one standardized format for all WDD data for the whole of the Northern North Sea, where it passed the QC check. We thought that we'd just be able to go in and use some kind of off-the-shelf technologies and take out ASCII formats and load them into maybe into a pandas data frame and push it up into the cloud. But it became a much more involved process than that. And rather than building a number of parsers for an unknown number of formats, we decided to take a machine learning approach to doing this. And the results that we got have been fairly good on that one. The well tops. So as I said, we took well tops from the OGA from the MPD and from the eight operators, which meant that the lexicons used were different. So we took those, we amalgamated them in a pre-processing step, and then we used a bag of word methodology and different NLP approaches to try and create something that was as standardized as possible across the whole data set. We did some alias mapping and some n-gram filtering and created a standardized data set per well. So that was the kind of associated tabular data. The main part of the project, I guess, that the partners were bothered about when looking for missed pay was joined well logs. So the considerations that we had for this was that the data sets are incomplete in terms of whether JWLs are available for all the wells in the Northern North Sea or not, and even where a JWL is not available for a well, there may be data missing even from the wellbore itself. The data is in spurious formats. I mean, we've got dlist, list, and las. The first two are much more difficult to deal with than the last file. And then we have data in TIFF format, which was out of scope for this project. We did get some data digitized, mainly CPIs. So we focused on the digital data itself and creating a joined well log using that. There were multiple, and I mean multiple versions of the truth. So we could have wells where you have, you know, 20, 30, 40 curves for the same well. Unsure about data provenance and the validity of that data. This is a difficult one to work with. You know, in a standard approach, you may go back to the source documentation and look at whether those curves match what you expect them to be. But we were unable to do that due to the high number of wells that we're dealing with. CPI data is key. They only had a small amount in the NDR, so we undertook a concerted effort to use a few analytical approaches to find that data within the NDR in the image format and get that digitized. So we're looking at the CPI data. We did a bit of well proximity analysis to try and focus on wells that weren't in an area that was highly clustered. It was important that the data coverage was as geographically spread as possible, rather than having you know, an already well explored field showing you know, showing a good data set. You know, we're looking for missed pay, not to explore in a field that's already got a lot of data. So when we were creating our curve joining kind of workflow, we had a number of considerations, and some of them are here. And this really started with us taking a process that we've been doing in Dataco more than Venture, and we've taken this over to the new company. We've been splicing curves and creating JWLs for petrophysicists probably for the last 15 years. So we've got a lot of experience in the steps in the process, but turning that from the kind of tacit knowledge that you would need to undertake this process day to day in a manual workflow and putting this into a digital workflow became quite a difficult process. And that's where we came to the curve joining methodology, basically a tree of possible outcomes using machine learning and more standard kind of approach to create something that is coherent from the top to the bottom of the well. So one of the key points of this was the curve validation. So we mapped around 1,300 mnemonic variations into the 7 that were delivered. We went through a sheet of, there must have been 13,000 different potential variations of mnemonics. We had 27 generic curve-specific QC metrics, which meant that we did around 15,000 individual quality checks throughout this process. And we created, I'm not sure that 1,101 is the correct number, but we created, I think it was around 1,200 JWLs in total, which we backward worked, that would be around 4,400 person hours or 587 man days of work to undertake this to the standard that we normally would. Whether or not there's a true parallel between the work that we would normally do and what we delivered as part of this data set is another question, but I think that it just shows that in a relatively short time, when the workflow took probably 2 days to complete, we're cutting down on the amount of time that was required to undertake this process quite a lot. So just to show you kind of a graphical representation of how we undertook this, we would load in all the data that was available, and then we would make a decision on which curves to use, using the process above and using machine learning classifications to try and pick the best curve. We would then pick which curves we wanted to use, and then splice those together using the standards that we use in house. Splice those together, and on the right hand side you can see the final curve that was created for delivery. So what did this look like in numbers? We created around 36 million feet of new JWL data. We checked around 1.7 million curves in this process. We joined 7,293 individual curves. We mapped around 200,000 curves in the whole process, creating 11,250 curves in total for the curves that you can see below there. So it wasn't only important that we delivered something that made sense, we also wanted to show the QC checks that we'd undertaken on the data and the provenance of the data itself. So as part of the last files that we delivered, we gave the names of the files that we used from the NDR dataset and a table of the data that was QC'd as part of this process to kind of give a complete audit trail of all the decisions that were made as part of this process. So what were the project outcomes? We delivered over 9,000 standardized well headers. We processed over 7,000 JWLs in total, making those standardized. So JWLs already existed. We made sure that the mnemonics, depths, and formats were standardized. We semi-standardized over 3,000 formation tops. We're working through 5,000 wells worth of key well reports with the data extraction and OCR. This is for the tabular extraction. We've passed, standardized and QC'd over 100 WDD formats for around 3,200 wellbores. We've joined over 1,000 wellbores worth of JWLs were created, and we digitized CPI logs for around 700 wellbores that didn't have CPIs before. So to wrap up on the data that we were dealing with, I'll go through some of the conclusions on the data quality that we saw within the data sets. And it's fair to say that when we're looking at it as a data set, it was great that all the data was available, but it was also quite a difficult data set to deal with. So we estimated that around between 10 and 20% of the UK NDR data is not accurately named or labeled. Around 30% of wells, this is anecdotal, but we think around 30% of wells were incomplete of what we would expect to see. And then the data formats and accessibility. as you can see below, we've kind of given, again, this is quite anecdotal, but also backed up by what we saw in the project, that, you know, over 50, maybe up to 75–80% of data is not digitally available. It requires some OCR or data extraction to be able to get hold of it and use it. And even at that point, it might not still be useful in the machine learning process, at least. And then data formats and accessibility. Data formats, a stronger standard in data formats would make this process much easier for everybody involved, I think. So some further challenges, two main points, I think. So the collaboration in getting the projects off the ground in the first place was, you know, it was a massive effort. And I think that the guys at the OGTC did a great job in managing to get, at the end, 8 different operators to deliver data. I think the OGA got involved in that as well, which is a great feat. And it was great to get our hands on that, but that was definitely a challenge and took quite a long time to get that together. In terms of the data quality and the data science compatibility, lack of provenance, wide range of data formats, as I already said, incorrect file formatting, and unstructured data locked into poor quality scans are probably the 4 takeaways that we've got. The MPD Blue Book standards, you know, it made it easier for us to understand the Norwegian data set. But again, it's not everything in there complies as it should to those standards. So what next? Well, we are trying with the whole part of this this project for us was that we would take something away that we were able to replicate, build on, and use elsewhere. So I'd just like to run you through some of the places that we've taken the technologies that we've used and kind of being able to expand on those. So we've taken parsers that we built as part of this project, and we've delivered data sets to 2 clients using this. We've augmented our current data extraction and QC process for 2 projects and built a data platform to sit that on to allow us to do large-scale data conditioning projects. For the JWL creation, the implementation of log splicing technologies onto a long-running project. We've been running this project for 15 years, and we're now looking at how we can take some of these technologies to create efficiencies and streamline that process. And as part of that, we have a roadmap to semi-automated log joining workflows to basically augment the process that we're working with and hopefully improve that process by over 20%. We also use the data set and some of the learnings that we had on that to run a proof of concept on NDR data and do a classification. We ran a POC on that and ran it over 100,000 documents within an oil company, and we highlighted over 7,000 candidates for data that should be in the NDR if it wasn't already there, and we're getting fairly good accuracy on that, kind of bringing down the timeframes of workflows that already exist to manually do this, to basically look over somebody's system and give them that information. So taking that and what we've already done, we're well into phase 2 of this project now. As I said before, there'll be a second data package made available probably later in the summer, maybe August, September time, I would think. And again, we're looking at the same two areas. So on the log data side, we're looking at improving our workflows, improving and maturing the curve picking, machine learning models, apply a thorough depth shifting and depth matching metrics. We would like to use the MPD data from that is joined to the Blue Book standard as kind of an analog to what good looks like and what it doesn't look like, so that we can publish some results on how good that data is. We would like to join all the curves available for the Northern North Sea, not just the wells that didn't have data available. So we have one set that covers that whole region. And yeah, we'll create a set of deliverables that will be made public to the Northern North Sea. That's already happening. That should be available this month, but there'll be a second set. For the tabular data, we are refining our workflows, improving machine learning, and extracting tabular data for the three key data types. And that's it from me. So I'll guess hand back to Ian.
Thank you very much, Chris. That was a very, very good talk. And I think, I think one thing you stressed there that, yeah, I think the OGA really helped us with these projects in getting that sort of enhanced data as such from the operators who participated in this project and provided the data. So yeah, we are very appreciative to the OGA for their help in pulling these projects together. So well, I guess there we go. It's time for some questions. There's been a few coming in on the chat, but does anybody want to raise their hand and ask a question to start off with, or otherwise I will just go to the ones which have been coming in on the chat function. Okay, so okay, well, we'll start with the chat. So first one here was from Per. Any progress with geochemical data, i.e. applied petroleum geochemistry? So I guess asking if we included any geochemical data within these projects. I guess the answer to that is no. We really concentrated on the sort of, dare we say, sort of standard log data to start off with, but I think it's a very good point, and it's something that I think we will certainly be looking at. Where do we take these projects next, and how can we incorporate other types of data to make more inferences on subsurface characterization?
Yeah, I think it's also worth mentioning that a lot of the technologies that we built should be applicable to other data types as well. So depending on what that data looks like, hopefully maybe there's some overlap there, but as you said, that wasn't part of the scope. So blunt answer is no, I guess.
Yeah. Okay, we have a few here from Inga. Could you please elaborate on how the best curves were chosen? And then it moves on to, was depth shifting done on the logs? If so, how was this implemented together with selecting the best log?
So picking the best curve. I mean, when you're a petrophysicist or when you know this data, knowing what the best curve is kind of inherent to the job. When you're trying to teach a computer what that looks like, it's very, first of all, very difficult, but also very nuanced. So we had to make assumptions on that. What we did as part of the workflow was we knew that the blue book practice in Norway was of a good enough standard that it was acceptable by those guys. So we actually took that as a training set for each curve type and built a machine learning model that basically gave us a scoring of the quality of the data based on what good and what bad looks like. And then we use that along with other mechanisms, depending on how long the runs were, what other data was available, and things like that. So that's how we picked the data, the best curves, I guess. In terms of depth shifting, no, we didn't do any depth shifting on this project yet. Phase 2, we are undertaking depth shifting. We created functionality to do the depth shifting, but we kind of ran out of time to implement that. So that's why, thankfully, the OGTC allowed us a bit more time to kind of work on that and implement that. So that should be along in the phase 2's data. And what was the third one? How was the implementation together? Okay, well, it wasn't, because we didn't do depth shifting as of yet, but we we understand that that is a drawback of the data. But we just wanted to deliver something that was better than nothing. I think that that's kind of where we got to at the end of this one. And then phase 2 will be looking at how we can enhance that and make it more applicable, probably more widely outside of a large scale machine learning project.
Okay, great. Any show of hands yet? No one willing to come in and ask a question? Oh, here we go. Alan Wilson. Here we go. Right, Alan, I am just about to unmute you. You should be able to speak now. Alan? Alan, are you there? Hello? Okay. Oh, oh, still muted. Okay, there we go. Unmute. No, working. Oh, technology. Don't you love it? Sorry, Alan, I can't seem to unmute you. If you'd like to put your, after requesting these things, if you'd like to put your, unless Hannah can help me out here.
I think he's just not accepted to unmute, so maybe just read a different question out. Okay,
so we've got the next one. Did you do any form of data inputting where we had missing logs? So I guess, was there any sort of, creation of missing data?
Yeah, so for the CPIs, both quick looks, I think they're called quick looks, and the proper CPIs, we got those digitized, as that was a key part of the workflows for both companies. So we got that data digitized, yes. We didn't use any technologies to do that. We used a third party.
Okay, sure. Will operators be chased by the OGA for the missing, incomplete, poor quality data? I'm
sure David would love to have a conversation with you about that.
I was going to say,
give him a ring.
If there's anybody from the OGA who is listening in and they'd like to raise their hand to answer that, that would be, they can. Oh, yes, here we go. David, you're on.
Hi, can you hear me?
Yep, loud and clear.
Okay, so yes, the OGA is always keen to get missing data and poor quality data replaced at the NDR. We tend to do it in a control sort of way, so particular data types. But clearly, it'll be a very, very difficult job. But we're always calling on companies. They've still got obligations to provide that data for the data prior to the Energy Act coming in. Certainly, going forwards, we're much better than we have been at getting the right sort of data. But yeah, in general, yes, but it's not going to be a huge push. I think the industry is not in a state where they can handle a big burden at the moment.
Okay, thank you very much, Dave. I'll put you back on mute. We have Dave. Dave Anderson. I'm just now allowing you to talk. If you would like to ask your question, I think you've got to unmute yourself. Can you unmute yourself, Dave, to ask a question? Oh no, hand's gone down. Okay, we'll go back to the chat. What constraints were used on the logs? So restrictions on the range of logs, constraints on sonic logs like demanding Poisson's ratio to be between 0 to 0.5, etc.
Yeah, so we did, I can't remember exactly what we did, but on the range of logs, Yes, we did a statistical QC, which was either a pass or a fail, and then kind of reworked and put back into the workflow. In terms of things that didn't pass that, so looking at the range of logs and whether readings fell outside of that and whether that was valid or not. Yes, that was part of the QC. So the QC, whereas that would normally be done by a person, was done statistically, and then that was followed up by somebody taking a look at it and either trying to work out whether the rule that we'd used was valid or not, or the curves that were being used were valid or not, and then making a decision on that.
Okay, thanks. Was any attempt made at removing poor data over, say, casing breaks?
Yeah, so that's a difficult one, and that's something that we were thinking about, whether we could use machine learning to try and find where the casing ends and that kind of thing. I was warned off that because it's a little bit more complicated than the assumptions that I was making. But the workflow that we used takes a section down to its deepest point and then takes the next weld down. So sorry, the next run down. So in theory, there should be a minimum amount of data that's within casing, and there shouldn't be too much. There shouldn't be any data that is run through casing, really. That's not to say that isn't the case. I think it's just a difficult process to deal with.
So do you think that's something that you might attempt in the future, or as you say, do you think it's something that maybe isn't?
I mean, I'm willing to listen to anybody's idea or approaches for that, because we had a few ideas. In terms of of things like that, there's a lot of extension that could be built on the kind of flow that we made. I mean, just the nature of digesting all the data and creating something that did what we wanted to do was probably the limits of where we got to. So these kind of extensions is what we will be looking at in phase 2, and that may become part of the scope for it if the feedback that we get is something that is critical to the data.
Mm-hmm.
If it's not, then it might be something that we just leave but use but caveat. So I'm interested to hear people's views on that kind of thing, because I'm not a petrophysicist, so I don't know whether it is right or wrong. And I think there's also a question of who is this data for? Because is it for a petrophysicist? If a petrophysicist wouldn't trust the data, then it's probably not for them. If it's for somebody doing a regional study, a geologist doing a regional study, and they would just take this kind of quick approach to creating a JWL, then maybe it's for them, and maybe that's something that they would accept. So I think it's kind of for us and for the wider community to understand where this data set may be applicable.
Okay, yeah, so we've got a few more minutes left. We've got about 5 minutes left for questions. We've got about 5 questions, so let's see if we can get through them. How did you check PDFs, TIFFs, etc. against ground truth?
I'm guessing this is about the tabular extraction. I mean, the nearest that we can do to that is we do a spot check at QC and make sure that the process that we're working with is good. I mean, the caveat on this is it going to be as good as sending it off to someone and having them type data in? Probably not. But there are certain things that we can do statistically. We can look at every OCR that you do comes back with a confidence score. So we have a check where we look at the confidence score of the data, whether that meets the minimum criteria or not. And if it doesn't, then it's discarded, because there's a difference between having an OCR of say plain text, where if there's a spelling mistake, it's not a massive deal. But if it's data, and you change a 1 for a 7, that could have big implications. So we're quite careful with that.
Okay, thank you. So we've got a couple of questions here. Second part of the first one is similar to another question, so I'll ask these together. Okay. How did you convert tables in the PDF docs that are images? Was any specific model used? And then where the sort of two questions overlap sort of. It says, is that model going to be available as part of the project? And the other one is, you know, are the codes used, are they going to be publicly available? So,
no, I think is a short answer on whether any of the code is made available. There may be some small parts of it that we'll look at publishing at a later date to kind of help people along these journeys. In terms of we're using a convolutional neural network to identify tables, and then we're rebuilding those. So maybe that explains enough. I think at a later date we may do a paper and presentation on that. I think it would be worth doing it. So you could maybe wait for that. Was there another part of that question, or was that it?
No, that was, I mean, yeah, I guess the thing to stress here is that, yeah, the techniques used, that wasn't really what is going to be made available as part of these projects. You know, that is at the discretion of the technology developers. It is their technology, and it's what they've been developing. It's really these projects were about making that data available and, you know, usable for the wider industry. Okay, so we just got a couple more to get through, a couple of minutes left. Regarding the review of, you know, sort of 100,000 unstructured documents, what's the outcome and indication of whether those documents would be candidates to report via the NDR, or whether those documents were missing from the NDR?
Yeah. So I think it, yeah, okay. So I think candidates is probably what we were talking about. It's not to say that they weren't already there. I wasn't fully involved in that project. So if Andy wants to come back and have a chat with us about that, I'm happy to do that.
Okay, thanks. Finally then, how did you deal with multiple sources of truth? You said it was impossible to cross-check every well.
Yeah, I mean, we can do a cross-check across single curves and give kind of a view of, is this the same data or not, and check whether something's on or off depth. Although we didn't fully implement that in this process. You know, we put this through a model that statistically gave us what it thought would be the best curves to use based on that, and a number of other criteria, and that's the best that we could do in this without spending, you know, a lot of time, which is kind of what we're trying to get away from, you know, expending man days to do this kind of work. We wanted a technology driven approach, so that's what we stuck to. We stuck to the brief to do this. So we could have cross-checked everything, but we did what we could do best, really, using the machine learning classifiers.
Yeah, I think it's a good point to make, that, you know, this is in these projects were really, you know, it's that sort of first step along a journey to really seeing the power and the implementation of these techniques, and really how they can, you know, be applied in an effective manner to help subsurface teams. Yeah,
and I mean, as I said, we've already found applications for this. The application for this, you know, in our own projects. Whether or not the application for this, as I've already said, is for a petrophysicist or anything like that is up for debate, and that's a debate that I'm willing to have if anybody's interested, because we want feedback on this and who thinks, you know, that there is application for this. But yeah, it's a technology approach that can be augmented, but it wasn't in this case.
Yeah, like I say, I mean, I will at the end of the webinar, I'll be putting up Chris's email address. So, you know, I say, you know, if you want to feed anything back to him, you know, we'll have any thoughts about, you know, where we could go with this, you know, I'm sure, like you say, I'll be really happy to hear from you, and, you know, and just carry on that conversation, please. So, yeah, that's great. That's our time up. So finally here we get one last one in about when will the new data set be available. I think Chris alluded to this within his talk. They're working on that at the moment, and we're looking at around sort of August, September time for the delivery of the next batch of the condition data.
Yeah, the first batch is the OJ have that. We haven't had any. We're still working with them probably on getting something that is ready to be released. So I would think over probably over the next 10 days, something like that. But just keep an eye on social media, I guess.
Yeah, exactly. We will post when that data is available. Okay, right. Well, thank you very much. Thank you very much, Chris. That was excellent presentation, and thank you very much for all the hard work you and your team has done on this project and continue to do. And we look forward to the next batch of results. Thank you very much. Okay, so now we would like to move on to the second presentation this afternoon, which is from Energective. And as we said at the beginning of this presentation, they looked at this challenge from end to end. So they took the same data that Chris and Sword had and applied their own data conditioning routines to that, and then they progressed on to doing the sort of automated analysis to identify pay. So yeah, I'd like to introduce Colin Frost and the team from Energective. Over to you, Colin.
Thank you very much, Ian, and good morning, good afternoon, everybody. I'm speaking to you from Houston, Texas today. I'm quite near a construction site here where I am, which is at home, so apologies if you hear any background noise. First of all, thank you again to the OGTC for giving us the opportunity to present today. Ian, Gillian, all your support, and the OGA for providing the data. David, thank you to you and your colleagues. And obviously we have several operators who really are the most important actors in all of this and the provision of their data. And everything we're about to talk to you is about providing something that should be useful to the industry in the North Sea. And the whole purpose of OGTC doing this was obviously to demonstrate what we're about to talk about for the economic benefit of the oil and gas industry. So we're going to be presenting to you, as Ian explained, the end-to-end process all the way through from the data conditioning, but also the application of machine learning to that. We'll be focusing on a particular set of algorithms there. There are other ways we can interpret the data, so please bear that in mind. And I also want to exhibit a little bit of humility on behalf of Energective at the front end of this. Is kind of, I feel a little bit odd and strange presenting to particularly operators on some of the findings that we've come up with on your oil field, your wells. And of course, I'll acknowledge right up front, you are the ones who understand your fields, your wells better than anyone else. And this project was done independently, largely independently of it with regard to interaction with operators. So it could be improved, I think, a whole lot more going forward with more collaboration and interaction with operators and the tribal knowledge and expertise that you would bring. So I'd like to make that point up front. However, that said, we've still got some very good, useful insights to share with you. And I think what we'll demonstrate is that we've managed to get, let's quote the 80-20 rule, maybe we've got 80% of the way there very quickly, very cheaply, and the remaining 20%. So what it does is it accelerates the process to find incremental reserves. Okay, without further ado, thank you. And I'd like to also introduce my colleagues. I have John Lobel, our head of geoscience, on the line with me. So this will be a team presentation. I have Krista Berry, who's also on the geoscience team, one of our senior experts, and we have Spencer Hanzik, who's our Director of Technology. Probably we had about half a dozen people in total working on this project. My role, Colin Frost, I'm a co-founder along with my business partner, Bob Lockwood, in Energective. And so I'm not going to be speaking very much. I'm going to hand over to the experts. Before I do that, if we could just advance one slide, John, please. What I'm going to do is just do a quick intro to us. There we go. So yeah, we consider ourselves to be digital formation specialists. So we help companies leverage the value of digital, which is obviously the hot topic these days. This slide just gives you an idea of the kind of firms that we work with, are working with, have worked with. We've worked with well over 100,000 wells over the years. Although our current form is probably just 3 years, we've got several years before that in doing a lot of data conditioning work. And you have some examples in the middle there. And with regard to our people, obviously our greatest asset, we've got a great blend ranging from data scientists, data managers to geoscientists and engineers. We have excellent program managers and change managers, because changing the way you work is obviously a critical piece of all of this. And we have great ties with academia and industry as well. On the left, I just want to point out, we don't just work with the oil and gas industry. You probably see United States Air Force research labs in there. We've been doing some digital twin work with them on fast jets, and American Bureau of Shipping. Again, we've been doing some work there. So very different to subsurface. And whilst we do focus on digital formation, obviously what we're about to present to you, and we're going to, if you can just move on, John, to the next slide. We can pick and choose from many different capabilities that get you to that digitally formed state. And we're going to be talking about some of these today. So there are three main things that we do to help our clients. And these are the three things here. So the first thing we do is we grab as much data as we can, whatever form it's in, however old it is, and whatever the state, good, bad, and we cleanse it, we condition it. That includes physical data, physical documents, includes electronic archive data, tapes, etc. So what you get from that is trusted data. And obviously that's in and of itself is useless unless you put it somewhere where people can easily get at it. So we put it in the cloud and we make it very, very easy for people to find and access across huge amounts of data, the data they need to solve a particular problem. That handover may take place for stage 3 for a particular workflow step, or for injection into a particular tool, particular analytics, just visualization. You might be just putting it into a dashboard or something like that, but it will go somewhere. And part 3 is really where all the value comes for companies. It's where the insight is seen, where it's interpreted, and where it helps you to reduce the risks of your decision making, accelerate your decision making, and basically run a much more efficient business with higher confidence, lower risk. So today we're talking about particular workflow. It's finding incremental reserves, subsurface, specifically bypass pay, behind pipe pay is what we're going to talk about largely. I just wanted to flash this up just to show you how quickly we can move. This is a startup oil and gas company that bought mature assets from Chevron in 2017. Their name is Cantium. They're in Gulf of Mexico. We helped them become a digital oil company from scratch, 75 offshore platforms, and just shows you the pace at which we can work. This project we're about to talk to you about is, you know the scope already. We're going to describe the end-to-end process, and we work with data on over 7,000 wells from both the UK and the Norwegian side. If you just move forward, John. This is our project timeline. We actually completed the whole end-to-end project last year. We did more work in less time than we were planning. We finished about 2.5 months ahead of plan, and originally we envisioned a 6-month duration. It took about 3.5 months. We did 500 more wells than planned, so 3,500 compared to 3,000. And the reason for that was originally one of the reasons was we originally phased the conditioning separately for LAS and raster logs, and that ended up being, we managed to collapse that into one. So we were delighted to move fairly quickly. If you move to the next slide, please, John. Yeah, the data conditioning side, we have a concept of data factory. So for this particular project, we were ingesting primarily well log information and conditioning it, doing splicing, removing end effects, step shifting, even doing synthetics. John will talk to you about that. Originally, we were planning to have seismic in scope, but that proved to be a lot more difficult than we anticipated. I think OGA and OGTC tried to get it for us, but I think the licensing side of that proved too problematic. The point with this is that we've got a factory, it's running all the time. There are 3,000 data quality rules applied depending on the type of data, continually improved, machine learning improvement all the time on those rules. And the purpose of trusted ground truth data sitting in that cloud there in the middle and enabling that to be disseminated to wherever it needs to be. Next slide, please, John. Ground truth is important. So we talk about provenance. Where did that ground truth data come from? Another word for it is master data. So part of what we've done here is we've looked at where there are duplicates and replications. Okay, where were they? Where did they come from? Which one did we choose? Why did we choose it? Here it is. If you want to know the history of how we got there, here's the history, and you can see all the originations of that data. So that's useful to know where your data came from. Okay, next slide, please. Obviously, the data is useless unless you can find it quickly and visualize it. So we put this data in some tools. Here's a screenshot of the North Sea showing the distribution of data across the North Sea area. Next slide, please. And a key aspect of this is when you look at your data and you want to know where it came from, you probably want to pull up the original document. So you can do that. And what we can do here with this tool is you can actually dissect the source data. And at the top, you can choose what data you want to see in a particular document. It could be a wellbore schematic. In this case, you're interested in logs. So show me the logs. And of course, a lot of the value is found in handwritten comments in these documents. So part of our process is OCRing handwriting, and you can go straight to it within the document. So this is a kind of overview of all the documents there, all the pages in the document, and you choose what types of pages you want to see and zoom into. At this point, I'm going to very quickly hand over to Spencer. I'm not going to go so much into the data conditioning details. Chris went through a lot of that. John and Krista will refer to it a little bit later on. But first, I want to hand over to Spencer. He'll just spend 5 minutes showing you the data, some of the data that we cleansed and conditioned, and how you can quickly get that data. And obviously, we want to work with the OGTC and OGA, maybe to, we want to provide a package of this data and the resulting insights to you. And we want to find a way perhaps of making it easy for you to access the data through some of these tools as well, maybe on a trial basis, something like that. We're going to have that chat later. But anyway, over to you, Spencer, and then we'll hand over to John and Krista for, I think, probably the most important part of the project. Over to you, Spencer.
Excellent. John, can you stop sharing so I can share my screen? So my name is Spencer Hondick. I'm the Director of Technology at Interjective. Let's see if I can share my screen. Can you see my screen?
Yeah.
Excellent. So what you're looking at is a QED find tool where you can search all the documents. So all this data is unstructured and PDFs, Word, and what we have an application that goes through, finds everything, rips everything apart, classifies everything automatically. So you can search everything very quickly. You can even do it by a map. So if a document has minutes, degrees, seconds, lat, long, you can kind of just search for all the documents in that area. So right now I just drew a little circle and it's telling me how many documents are in this area. And it automatically found all this location info already in the document. So if you're looking for, I don't know, a gamma ray, so you can type in just gamma ray at the bottom. And I'm gonna try not to go too fast because my application goes really fast and sometimes the internet doesn't move quick enough. So you can type in gamma ray and it will search for all documents that have the word gamma ray in that little search area that you have chosen. And right now it's pulling up 590 results in 1.7 of a second. So it's searching through like hundreds of thousands of files. I don't know how many files are exactly in here, but it's searching through, you know, you can even search through millions of files in seconds. We have clients that we can search really, really quickly. And you can tell right here that it's finding TIFF files that are well logs and you can download them to your computer and you can view them. What we can do is, let me move the shape. You can literally type in anything you want. So I'm gonna write in a well name that I kind of know of, and I'm gonna mistype it. We're gonna call it 13/27, and let me zoom in a little bit so you can see this a little bit better. There we go. And so you can search this, and what it'll do is it will find all documents associated with it. So it searched all documents, including its text, the images, everything has been OCR'd. Even if you attach an image in an email, if we had emails, we could search that too. So right now it's searching everything that we see right now. And what you can do is also go, okay, I want to find a end of well report. End of well report. So you can find an end of well report. Let's pick the first one. Why not? So what this will do is I clicked QD Res, RV. So what it will do, it will take apart, it'll take that whole document, download it, rip it all apart, and classify every single page for us. And we built this in a way where it makes low quality images. So for someone who's offshore on a platform, they can see all the data really quickly and not you know, question it, and they see all the data before actually downloading a gigantic PDF to their computer. Now I'm trying to wait for it to download. Hopefully it downloads. Well, there it goes. Okay, so right now it ripped everything apart and it structured everything for you. So you can now see every single page, and let's say you're looking for the well log in this document. You can just choose well log and it will tell you exactly where the well log is. It's classifying every single page, everything in this whole entire document. When you put this in the cloud in the data lake, it will actually go 10 times faster because it can use cloud computing. So you can say, oh, I want to see all the tables. Here's all the table structures. If you want to see a title page, here are the title pages. So you can see everything really, really quickly and not have to download the whole entire document instantly. You can just view it. So you can click, choose this and it will bring it up. You can also use NLP. So we have this application where you can ask a document questions and it will tell you an answer. So right now it's gonna load and it's gonna load the document for me. So you can ask it a question itself. So one of the questions, I think most well reports, I hope this has an answer. Why was this location proposed? There we go. And it's searching. So it's finding why this location was proposed. So it's saying that this location was proposed because of this. And what we can do is we can kind of highlight that and, you know, search for that in here and zoom in right here. So you can see that why this location was proposed. And you can see it's in a sentence and it's telling you why it's proposed. You can even ask, what block is this well in? So it figured out the block and it said in 1327A. So it's telling you where it is, what block it is. You can ask it questions. It's running NLP, natural language processing, and it's all doing it automatically. And like as you can tell, it did it instantaneously, and it was doing 79 pages instantaneously because it's using cloud computing. You can even go, like if you're looking for a last file, and what we made this one for was to help offshore guys when they're looking for something. So let's look for a gamma ray, because I like looking for gamma rays. Let's look for that, and let's look for not a PDF. Let's look for a certain file type. Let's look for a LAS. So we can click on LAS and say search. And you can search, here we go. We have a whole bunch of LAS files. I'm gonna choose one. And what it'll do is it'll take apart that whole entire LAS file, tell you all the metadata for it without actually you downloading the whole LAS file. So here's all the curves for this LAS file. It will tell you all the metadata about this LAS file. It'll tell you all the information about it, and you can even download all this information. Now you don't have to like go figure out how to download it on yourself. You can automatically click on it and it will let you download it. And it'll give you a quick preview of this LAS file that you've just chosen. It'll give you like a quick thing so you can go, oh, is this the one I'm looking for? Is this exactly what I'm trying to go for? And what we have right here is this a whole bunch of unstructured data that we can combine together. We even have an application where we take structured data and unstructured data and combine it together. So it looks like I'm running out of time. I'm gonna route back to John, and if we have more questions, you can ask me at the end of this presentation. All right, John, you can share again. Okay, John, you can take it from here.
Okay, so we've been through the company and the demo. I'm going to jump right in here to basically the log conditioning, and we're going to go through our analysis. But I'm going to jump right to the conclusion first. So we digitized and analyzed about 35,000 different sets of data, LAS, rasters, etc. We apply a number of different analytical tools in our conditioning and our petrophysical analysis. We derive petrophysical parameters. We identified some thin bed hydrocarbon pay using a Thomas Steiber method. And you know, in our first pass here, we identified about 1.7 million barrels per acre in the North Sea. So, you know, hundreds of millions of barrels in bypass pay areas. Now, they're small, etc. But we started off here. We acquired the data. We conditioned it. I'm going to go through some of these pieces. We're going to take a very geoscience-based run at this. We have we have a number of people in our company here are geophysical based, geoscience based. So we have a petrophysicist that's got almost 30 years of experience who has written all of this petrophysical code and adds to us on a daily basis. So we have something we call expert aided automation. So all of our processes are designed to be automated, but they're checked, they're double checked, they're QC'd, and they're expertly defined. We have a petrophysical evaluation. We ran Thomas Steiber evaluation here to look for thin bed pay or bypass pay. We also did conventional petrophysics. We have a philosophy that we run Thomas Steiber everywhere. To go through a screening process and determine where's Thomas Steiber should be applied, you might as well just apply it. Thomas Steiber does not find anything that's not already conventional. So it just adds. So it doesn't subtract from conventional. And we did a geophysical prediction. We can't help ourselves. We are all people who have worked in the exploration and development business. We have all worked for operators throughout the world. It only made sense that while we were here, we should predict sonics densities, shear wave velocities, and make synthetics. To aid in our petrophysical evaluation, we did some sequence stratigraphic analysis as well, and we have an automated method for picking tops, so we did that. Here's our opportunity summary. So we had a total of 3,888 wells. We had 441 of those with Thomas Steiber evaluation, 131 of them. And if you notice here, about an average of 35% of all the wells found some bypassed pay. And these are 68 wells that had greater than 20 feet of bypassed pay. We composited logs for 3,486 wells. We have one set of curves. They're depth tied, they're casing corrected, they're QC'd and edited. They have full petrophysical evaluation where the logs existed. And we have a data set with a single petrophysical analysis. We have Thomas Steiber on selected 446, and we'll tell you why we only use that many. That criteria was Thomas Steiber is looking for where the deep resistivity curves have oversampled or have not seen the resolution, did not have the resolution to see thin beds. So it's a process for that. So we looked for vertical and near vertical well bores that had less than 20 degrees of deviation, we wanted wells that had a lot of stratigraphic and geologic interval represented. We wanted to cover the entire geographical area, had good quality and availability of logs, and any value adding information that had core tests, dip meters, etc. Our geophysical log is rock physics based, so we're going to reconstruct the rock's VPVS and density from its mineral constituents, and we're going to make a synthetic seismogram in depth. And we did some plate fairway maps. The value of our product. Our product is done with a single petrophysical philosophy and a consistent model. We are not saying we have the 100% solution and you can go off on these and contract with a drill rig and start working. This is an 80% solution that is consistent over the whole area. It allows a company's petrophysicists or geoscientists to pick it up and use their expertise to deep dive in very detailed and company-specific objectives. We have a full set of consistent edits and splices. We have a basin-wide consistent analysis. We have a single pay cutoff. So we have calculated pay using a cutoff. It's not your cutoff. It's a general one over the whole area, but the raw logs are given back. So you have all the raw water saturation, porosity, and V shale curves, as well as 12 Thomas Steiber curves. So the laminated versus dispersed clays, etc., and the sands. So, and we provide a sonic density and synthetic. We've run something that was published in 2018 called quantitative sequence stratigraphy. We provided those as well for these wells, and a viewer tied to biostrat and consistent assumptions. Okay, so we start off, we bring it into the lake, into our data lake. As I said, we had 3,883 wells. We started with 33,000 digital well logs and almost 80,000 images. We started looking at their data quality. We break down the completeness by block and the completeness and metrics to prioritize the blocks. So here's our data cleansing conditioning workflow. We've applied this to over 100,000 wells worldwide and something approaching 1 million curves worldwide. On 6 continents. We have relative well data. It's integrated and cleansed, digital, raster, and paper. They're organized into folders, and a LAF format log is composited. We have a unified curve name and units. They're depth shifted. They're removing casing effects. They're spliced. They're removing invalid values. And we use neural networks to fill in the missing data sets. And You know, for example, Colin gave an example in the Gulf of Mexico. We did almost 3,000 wells in the Gulf of Mexico. Only 256 of them even had a porosity log. They were old, 50-plus-year-old wells. They only had an SP and 3 resistivity curves. We successfully neural network predicted porosities for all of them so we could run this. And then we convert some non-LS data to digital. These are our composited curve names here, and there's what's been put out into the database. These are all of the wells in here with the wireline or LWD data. Okay. Again, Chris talked a lot about conditioning, so we'll just go over here. We have algorithms that do this. We have most of this process is automated, and it's automated and defined by a petrophysicist. So he automates it, he QCs the work, and we have a group of companies that do this in the factory method that Colin showed earlier. Okay, so we have, this is our automation process. So this is our interpretation. So it's an expert assisted automation. That says everything is checked here. So we start off. So here's our process again in the petrophysical side. So we neural networkly predict sonics and densities for complete porosity log coverage. So we get logs where there weren't any. So we have top to bottom. If you have a log there of any kind, we now have a porosity, water saturation, and V shale curve in that for that. Do a petrophysical evaluation, full conventional petrophysics, dominantly using Archie's equation or a modified Archie's equation. And we run Thomas-Steiber evaluation and our geophysical prediction and QSS. I told you how we picked these earlier. Here's our petrophysical workflow. We are using a methodology here. Our E2A, our expert-aided automation, is a combination of geostatistics and neural networks. So I have worked in both for the last 25 years in mobile research. So I worked on original product called SigmaView that was with Western, and on Emerge that went to Hampson Russell. So we look at how you move away from control using a variogram to define that and to minimize that error. As we get outside of that, that's propagated through our data set. When the error exceeds what we've set as limits or the variogram limits, then it requires additional input from us. So we do that, we create our V shales and lithology columns that way, and then we QC. We define our petrophysical zonation. We customize our code to calculate petrophysical parameters in QC, and then we rerun manually when we find problems. We're checking all the time. So there's been some questions. We are looking at cross plots all the time. We're looking at comparing one curve to the other, etc. And then the Thomas-Steiber method is we have to set 100% clean and 100% shale endpoint, and that's done for each discrete sand package in all the wells. And then we tabulate that into a spreadsheet. Again, we know Thomas-Steiber is not applicable everywhere. However, it adds to conventional pay, does not exclude it, so it's faster to include all of it and filter false positive on a much smaller subset. Okay, so here's our detailed wells. These are the 446 that we analyzed for Thomas-Steiber, again, based on number one being regionally extensive, covering the area, etc., and not being very close vertical or very close to vertical. For those of you who don't know Thomas-Steiber methodology, what you're doing is you're looking for laminated sands. So you're trying to define the differences between dispersed clays like this, where the clay is in the pore space, and structural clays, which is where the clay has replaced the grain, versus laminated, where we have thin shales in between good sand. And these have been found around the world to produce, when you can find them, to produce very good rates, and usually very low water cuts. We are dominantly dealing here with the dispersed clay, and you can notice that this dispersed clay from the original paper goes down to 30% dispersed clay. What we want is things along this center line here. Structural clays, we're not seeing a lot of that in this study. So what we get out of this is it's basically a set of curves like this. So we get conventional porosity, then we get sandstone matrix, then we get dispersed shales and laminated shales. So the white in here is the added Thomas Steiber laminated porosities. And that's what we're identifying. So here's just a typical display coming out of what we look at in QC with. So we can see we have normal petrophysical logs here, SP, density, neutron, gamma ray, our hydrocarbon densities, etc., our RWs. These are the cutoffs for Thomas Steiber. And what we get is a conventional porosity and a Thomas Steiber improved porosity in here, conventional V shale and a Thomas Steiber V shale, which is sand laminated. And then we get our pay. So our conventional pay is these gold bars here, and the Thomas Steiber is the orange. So we get uplift in here of some Thomas Steiber pay. And if you notice on this dispersed clay, we're only going down. So we're only looking at this top 10% of these dispersed clays. Here's another well. And again, depending on the well and depending on the rocks, we can change these cutoffs to fit. This is one that would have been manually corrected. So this well didn't have hardly any conventional pay and had quite a lot of Thomas Steiber pay. Okay, our geophysical logs. So we use basic rock physics. As we're going along, we build a rock physics database of those different clays, and we arithmetically sum the VP to be made up of the percentage of that clay, the percentage of the mineral constituent and its densities and its bulk modulus and shear modulus, and we create these logs. So here is a geophysical prediction. So we have our gamma ray, our lithologies. There's a shear wave, a DT compressional log there in gray, and the red is our synthetic sonic. Now, in the density, the gray is the composited density. We don't have any density log above this point, and we have casing effects in here. So we've predicted that there and make a synthetic out there. That's provided for every well where we have data. Now, just part of a previous case history, but we have found that when we use our geophysical predicted logs and conditioned seismic data, we get extremely high quality ties up into the 0.9% here. Whereas previously, without conditioned logs or conditioned seismic, we get ties that sit down in here. We have a workflow for TOPS and sequence stratigraphy. So we establish regional settings. We do this exactly the same way. We start off at control. We pick them. We tie biostrat to them. And then we start off with our well subset. We correlate. We work out. And as we run out of things, we generalize, update the V-shale as part of our petrophysical initiative. The V-shale and sequence stratigraphy builders used to create these sequence stratigraphic plots, this QSS data set. We're dominantly picking third orders here. So here's just an example. Here's our V-shale log and some sequence stratigraphic interpretations. What we're using is this quantitative sequence stratigraphy. So we are calculating it. It's mathematical. It's run in our as we're processing our data set. So as we're picking maximum flooding surfaces and sequence boundaries. So and we, as I said, we're dominantly looking for third order sequences. What we want is we're trying to find the lower the value, the richer the sand content. So we're trying to find these different pieces in here of this is an automated QSS. So we have multiple, and then we put out cross sections of these. When we have seismic, we tie them to seismic, and this is how we QC things. Again, we can have different order cycles. So we can have either a third order or even a fifth order, depending on the detail and the parameterization that we put out. But if you look at that, the QSS tends to be almost the same. We've done this because we wanted to make sure that we were not only looking at lithostratigraphic information, but sequence stratigraphic information. So we wanted to make the difference. We automatically pick our tops using a lithostratigraphic base. We use a correlation. We look at the log curve, the shape of that log curve, the breaks in that log curve. We pick the tops and the bases. So we wanted to make sure that when we were doing Thomas Steiber and other analysis, that we had both a lithostratigraphic and a sequence stratigraphic framework. Okay, so we've been through this. This is our opportunities. Again, I went over that at the beginning just to hit it again. We identified 131 wells that had some Thomas Steiber sequence stratigraphic, or some Thomas Steiber pay in them, and we had 68 of those wells that had greater than 20 feet. So here's our opportunities. These are the red dots, are the areas that have been identified, and these here are the wells with effective Thomas Steiber pay over 20 feet. Sorry. Okay. We looked at licensed and unlicensed. So a large majority of our wells with bypass pay greater than 20 feet are in licensed blocks. Okay, now just another one. Here was our full analysis where we're looking at not only lithostratigraphic tops Thomas Steiber, but we have sequence strat here. And if we zoom in on one of them, we can see our sequence boundaries and our maximum flooding source. And just again, we can also vary our Thomas Steiber cutoffs if we see different both sequence stratigraphic and lithostratigraphic zones. That's the manual QC that comes after the process. Okay. Finally, we have a tool. We have our own tool, but we look at our data set like this. So here we're able to look at as many wells as we want. We're doing, again, the geostatistical base situation. So we picked this well, and then these are all the wells as they get further and further and further away from that well. So we're able to do that. We're able to change V-shale porosity and water saturations and see how and put our tops on here and put our QSS on here and see how good we're doing. This is part of our QC tool. If we start to change V-shales and porosities, and we can also change Thomas Steiber parameters, we can start to see how some of these zones are correlating with each other. And the Thomas Steiber was our methodology to find overlooked bypass pay. The synthetics was not part of the original mandate, but we did it anyway because we feel like it's a normal part of the workflow. A lot of the add-ons here, the QSS was not part of the original mandate, but we added that to try to improve our interpretation process and to improve the product here. As I said, we're dominantly all explorationists, geologists, geophysicists, petrophysicists who work with data scientists instead of the other way around. And we we know what a workflow should look like. We know what, as if we were exploring this area, what we would like this to look like. And this is just a final one of our wellbore utilities where we can actually put in well costs, completions, etc., recovery factors, price, and risk. So, and get them to light up as well. Okay, just a final set of slides here. As Colin said earlier, we wanted to work with seismic data to begin with, but it didn't come. We have a full seismic workflow here as well, where we can automatically pick tops, faults, horizons, sequence boundaries. We can build, we have full geomechanical processes, both in petrophysics and in seismic, that we can build, you know, earth models. Okay, Krista? Hello?
Hello, can you hear me?
Yeah.
Hello, okay, thank you. Okay, so I just wanted to show a quick example of kind of where we would like to go after doing a project like this. And this is collaborating with the operator to get that last 20% of the solution. So talking to an operator in Western Canada, they had a field that they were saying, you know, was tired, mature. They needed to figure out next steps. They weren't sure what they were going to do with it. And so after talking, we realized that the producing formations fell within the geological environments that are favorable for Thomas Diver. So it's kind of the perfect opportunity for a pilot project in that basin. Next. So this is the study area. It's an area called Redwater. The study consisted of 22 wells with a vintage of 1978 to 2011. Moving through our workflow, we were able to identify 3 main things to move forward with testing. And what was really valuable with this was the analysis itself, the automation, Thomas Diver and petrophysical curves, was very, very quick. We were able to get the results to the operator, you know, within a day type thing. And then collaborate with them real time, reservoir engineers, geoscientists, to actually program opportunities to go test almost immediately. So we're going to look at 3 of those in detail. One was looking at, so this very first one was a vertical well that had been drilled in the 70s. So we went back in, tested the upper portion here that was identified with the Thomas Diver bypass pay. And it tested 11 BOEs per day in that upper perf. So that doesn't seem like much, but in Western Canada, operators are going through looking for low resistivity pay for potential places to bring in multilaterals. So that's very important. And so we've been able to identify this in not only this formation, but in other formations that are low resistivity pay. The second example that we were able to help them out with was a recompletion opportunity. Originally, the well was perforated and tested with no inflow, but you know, it looks pretty great. So upon this analysis and seeing, yeah, you know, there is some potential here, we went back in, got an additional pressure, and realized that the reservoir was actually virgin pressure. So that we are planning to go and re-stimulate that well. Next slide. The third opportunity was an upper channel that hasn't really been taken advantage of right now. And you know, we've run the same water salinity over the entire Manville section. So we know that even though we're not seeing a big uplift with Thomas Diver here, it's actually underrepresented because we need to use a different water salinity. But that still gives us good indications that this is probably going to be successful. So the operator's planning to move forward with this test case as well. So the important thing to note is that we were able to move very quickly. It was basically 3 days from the start of the project to getting some results, to talking, collaborating with the operator, going back in, adding in their expertise for certain wells to get a better picture, getting their inputs on things like salinities and what their pay cutoffs were for the area. And we came out with some really interesting things that they can move forward on this very tired area. Next. Okay, so I put this together because historically, I think this is pretty interesting. So this graph shows how it's based on seismic technology, but how seismic technology correlates with the number of wells drilled per year in this one particular very tired field since 1966. So the most noted correlations occur post Apache acquisition in 2000. Since then, 49% of the field has been covered in 3D, which was the first, what we're calling the first technology wave, followed by post-stack merge technology, which we're calling the second wave, and then pre-stack merge technology and 5G interpolation technology. When we overlay these trends with historical oil prices, we see there's a direct correlation between low oil prices and an implementation of new technologies. And the ramp up of wells drilled as that technology becomes efficient. So finally, what we think is that all these machine learning algorithms and the AI driven knowledge application is our anticipated next wave. So by perfecting this now, we're really setting ourselves up for the point where we get back to high oil prices, and then companies will have their inventory ready to go. Thanks.
Just our summary and conclusions here, same as you saw before. And we'd just like to thank you for your attention. And you can ask us questions here, or you can reply to Colin and any of us as well.
Hi, well, thank you very much, John, Colin, and the rest of the team. That was a very thorough presentation, and very interesting to see how you've approached the challenge. So we have time for a few questions, and they've been coming in on the chat here. So we'll just, I guess, just crack on with those. The first one which came through was, do you have recommendations on how the data should be reported from the operators, such that data may be easily used in a data science pipeline?
Yeah, I would. So just
quickly
from a data factory point of view, yeah, we have recommendations for standardizing the way in which data can be captured more efficiently and standardized. We call that the point forward solution, and definitely we plan to share those recommendations with OGTC and OGA, and hopefully that will be useful. I know the OGA are looking to revamp their national data repository, so hopefully those recommendations will be useful going forward.
Okay, thank you. The second one here is, have you done blind tests on the editing procedure based on a machine learning model? If so, how good was the accuracy?
Okay, so we've done, so I guess in the conditioning, we do some blind test. We do, again, my background is with neural networks and eMERGE. So we do a lot of cross-validation. So we do a lot of removing data set and repredicting it. We both do that uphole and downhole when we're predicting data sets in petrophysical, and definitely in areas where we expect problems like casing corrections and also where we have depth shifting, etc. So we do that kind of blind testing. We have a threshold. We will not go below 85%, but we prefer to be above 90% on that.
Okay. Thank you. So what's the next one coming through here? Let's find it. It's been quite a Quite a bit of action on the chat here this afternoon.
So there's a question about mineral models. So
Yeah.
if you saw on our sheet there, we both have smectite and illite as bulk modules, shear modules, and density. And so we would dominate so we kind of try to interweave all of these processes together. So we desperately try not to silo. So those type of transformations will usually occur in the structural clay part of this, of the Thomas Steiber diagram, diamond as we call it. So when we see higher than normal structural clays in there, then we assume that they're this. And Tom, the petrophysicist, uses some depth dependence to modulate that. We're probably not doing 100% of that job. As I said, we are doing this on a bulk rate, 3,500 wells in 90 days, start to stop. So, I mean, that would be, that's about the best we can do. But we can tend to see them and identify where they are and then use those bulk modules, shear modules.
Okay, thank you. Have you seen, sorry, John, I seem to have lost my window at the moment. So if you could have a look through.
Do you have some anomaly detection in the log curves before moving ahead in the conventional petrophysical evaluation? Gamma ray neutron porosities are often affected due to environmental factors. Are these curves edited before using them for the analysis? Definitely. Because of Colin showed you that we get all of the information from the log headers, so they're all environmentally corrected in the front end of our process here. So we in effect start all of this with environmentally corrected gamma ray and porosities. So our EGR is our main input to things before we even go to V shale. About the sensitivity our analysts, so that's one of the reasons we separated them out geographically or made sure we had geographical coverage, was we were trying to, facies is probably more detailed than we wanted to do, that we intended to do, but we looked at them on a lithostratigraphic boundaries and sequence stratigraphic boundaries. For Thomas Steiber, we parameterize based on those pieces. As I showed you, there was one well that had lots of different endpoints. And that would have been a manual process. That well would have started with iterating and converging on an answer. So our iteration and our convergence tends to be that we want to get close to the conventional piece anyway, because there's probably, well, we basically emphatically say there's no conventional pay in a clastic that doesn't meet Thomas Steiber cutoffs, because all we're looking for are still our clean sands. So hopefully that helps. While predicting densities from sonics or vice versa, how do you take care of the prevailing anisotropy that may affect data? Oh, excellent question. Again, a lot of we tend to put our strongest case in the vertical and near vertical wells. That's why they were presented here as the only really results that we had any kind of great confidence in, for this exact reason. And I have to say, we're still trying to figure that out. I mean, we can correct for deviation, but at this point in time, we're having, we have to figure out how to predict, how to use machine language to get to true stratigraphic thicknesses, which is just directly in line with your question. Now, we don't predict density from sonic. We predict density from Sonic and all of the other logs so that we have. So we tend to use a classic, a classic deep resistivity to Sonic transformation or Sonic to density Gardner's equation are classic, but we're using a neural network view. So we're including a bit of gamma ray. We're trying to include a standard set of logs that we can get, which we had here, which we get neutron porosity here, we get gamma ray. Dominantly, we have density and some densities and some sonics. The next one, missing pay that does not follow Thomas Steiber. We didn't, we took this approach and that was it. We thought about doing low res, and we found at this point in time, we probably have to say, we're not there yet. When you're doing 35,000 curves or 3,800 wells, and you try a low res algorithm, you probably can identify an awful lot of pay that's not pay. And that's what we were trying to stay away from. We really didn't want to identify false positives. We didn't want to come in and say, oh, we found a whole bunch of stuff here and have it all, kind of wash out as being no good. So we took a conservative viewpoint using Thomas Steiber, and we took the viewpoint that in a class stake, anything that's Thomas Steiber would also be conventional. So we can stay along the lines. We didn't have to push any major algorithms. Low res or other types of algorithms would be great. But we haven't done that yet.
Just gonna say, John, Colin, we have sort of run out of time really for the allotted time for this webinar today. I think, there's
only, Ian, there's 2 questions left. If you can, I can answer them real quick.
Oh, okay. You can do them pretty quick. Yeah. I think this has been really fascinating, the questions. This has been some good conversation on these.
So what does our data package include? It includes all of our corrected logs, all of our composite logs, our V-shell water saturation and porosity, and 10 different Thomas Steiber curves. If you know much about Thomas Steiber, there's a laminated versus dispersed clay ratios, and there's pure laminate, pure sandstone V-shales, etc. All of them are there. The other one, do you have a workflow to integrate the Thomas Steiber bypass pay with DHIs? So Hector, I worked in DHIs or AVO in 1981 in a research lab before it was known. So everything I do has DHIs in the back of my brain. So unfortunately, it's like part of my DNA. Good question. We don't have any seismic. So in other places, definitely. When we work in the Gulf and when we work in other places, we modulate it. We risk Thomas Steiber bypass pay identification with direct hydrocarbon indicators. But we don't have any seismic here.
And I think, that's an avenue that possibly we would like to pursue going forward. We had to sort of say, I think it was addressed at the start of this about trying to get seismic data along with this. But at the time, that was proving a little too problematical, and we wanted to, to kick these projects off, but I think it's, it's certainly an area that we would potentially look to now we've done these projects, is how do we enhance and integrate more data into, the area that we're, this sort of pilot study area. Okay, is that us? Okay, well, I think all that leaves me to say is thank you to our presenters today, Chris from Sword Venture and Colin and his team from Energective. I think, there's been a great insight into the work they've done. And you know, I think, you know, from the OGTC point of view, you know, we're really happy and excited about, you know, the work that's been done, and you know, and really where this can go next is what we really want to look into and investigate. So as I've got up here, you can see, I mean, sorry we had limited time today for sort of questions. I mean, I'm sure, we could go on longer with this, but as you can see, we've got some contact details up on the screen at the moment. Please feel free to contact either Christopher, Colin, or myself if you have any further questions and about projects or about what you've heard today. And I guess the last thing to say is the second part, which will again focus on the automated interpretation and data analytics, will be on Tuesday the 9th of June at 2 p.m. Hope to see a lot of you there again on Tuesday. So again, once again, thank you very much for joining us, and hope everyone enjoys the rest of their days. Thank you very much.